A flash of light tore through the universe when it was still young, silent, and barely recognizable. That light began its journey before our sun existed, before Earth formed, before most galaxies were born. For billions of years it traveled through expanding space, stretched, slowed, and hidden, until now. What died back then has just revealed itself, and its story is rewriting what we thought we knew about the first stars. Look up at the night sky. Every single point of light you see is a star, and every single one of them is fighting a battle they will eventually lose. This is not poetry. This is physics. And the moment they lose that battle, some of them detonate with such unimaginable violence that they outshine entire galaxies. We call these explosions supernovas. But to understand why stars explode, we need to understand why they exist in the first place, and more importantly, why they must die. Stars are not eternal. They are born, they live, and they die. And their death is written into the very laws that give them life. Let me explain something that might change how you see the universe. Every star, from the smallest dim red dwarf to the most massive blue supergiant, is locked in a constant war. On one side, there is gravity, relentlessly pulling everything inward, trying to crush the star into a single point. On the other side, there is energy, explosive and fierce, pushing outward from the core, resisting that collapse. This is not a metaphor. This is literally happening inside every star, every second, for billions of years. Gravity wants to destroy. Energy refuses to let it. And for most of a star's life, these two forces are perfectly balanced. Imagine holding a balloon underwater. The air inside pushes out, the water pressure pushes in. Release either force, and the balloon changes instantly. Stars work the same way. Gravity is the water, energy is the air, and as long as both are equal, the star stays stable. This delicate balance is what keeps a star alive for millions, sometimes billions of years. But that balance depends entirely on one thing: fuel. And fuel does not last forever. Now, let me give you some perspective. Our Sun, the star that makes life on Earth possible, is classified as a G2V yellow dwarf main sequence star. It is a medium-sized, middle-aged star sitting comfortably in what astronomers call the main sequence, the longest and most stable phase of stellar life. The Sun is so large that you could fit 1 million Earths inside it. 1 million. Think about that for a moment. Every mountain, every ocean, every city, every person who has ever lived, all fitting inside the Sun 1 million times over. And yet, compared to the universe, our Sun is considered average. In some cases, it is even called small. There are stars out there that make our Sun look like a grain of sand on a beach. Blue giants, red supergiants, hypergiants so massive that if you place them where our Sun is, they would swallow Mercury, Venus, Earth, Mars, and stretch past Jupiter. These are the monsters of the cosmos, and the bigger the star, the more dramatic its death. Because here is the rule that governs everything. A star's size determines how it will die. Small stars like red dwarfs fade slowly over trillions of years. They cool down, dim, and eventually become cold, dark remnants called black dwarfs. They die quietly, without fanfare. Medium stars like our Sun swell into red giants, shed their outer layers and leave behind dense cores called white dwarfs. They die beautifully but gently. But massive stars, stars that are 10, 20, 50 times heavier than the Sun, they do not fade. They do not dim. They explode. And when they explode, they do so with a force so extreme that the explosion can be seen from billions of light years away. That explosion is a supernova. But why does this happen? Why do massive stars explode while smaller ones just fade away? The answer lies in fuel. Stars are not powered by fire. They are not burning in the way a candle burns. They are powered by something far more powerful: nuclear fusion, and fusion requires fuel. For most of a star's life, that fuel is hydrogen, the simplest and most abundant element in the universe. Hydrogen is fused in the core under crushing pressure and heat, creating helium and releasing energy. That energy is what produces light. That energy is what pushes outward against gravity. That energy is what keeps the star alive. But here is the problem. Fusion is not infinite. Hydrogen runs out, and when it does, the star must find another fuel source or die. Smaller stars cannot generate enough heat and pressure to fuse anything heavier than helium, so they simply stop. The outward pressure disappears. Gravity takes over. The star contracts, cools, and fades. But massive stars are different. When they run out of hydrogen, they do not stop. They get hotter. They start fusing helium into carbon and oxygen, then carbon into neon, then neon into magnesium, then magnesium into silicon, and finally silicon into iron. Each stage produces less energy than the one before. Each stage burns faster. Hydrogen fusion can last billions of years. Helium fusion lasts a few million. Carbon fusion lasts a few thousand. Silicon fusion lasts one day, one single day. And then it is over. Because iron is different. Iron cannot be fused into anything heavier without consuming energy instead of releasing it. Iron is the end of the line. The moment a massive star's core turns to iron, the outward pressure stops, and in that instant, gravity wins. The core collapses, not slowly, not gradually. In less than a second, a core the size of Earth is crushed into a ball the size of a city. The collapse is so violent that it rebounds, sending a shockwave tearing through the star. The outer layers are blasted into space at speeds exceeding 10% the speed of light. The star explodes. And that explosion is so bright, so energetic, that for a brief moment a single dying star can outshine an entire galaxy of hundreds of billions of stars. This is a supernova. And it is not just destruction, it is creation. Because in that explosion, elements heavier than iron are forged. Gold, silver, platinum, uranium. Every atom of gold in every ring, every coin, every circuit board was created in the death of a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stars that died billions of years ago. You are made of stardust, not poetically, literally. Stars do not just die, they give birth to the next generation. Their explosions seed space with the raw materials needed to form new stars, new planets, and eventually life. Without supernovas, there would be no Earth, no oceans, no air, no you. Death and creation are inseparable in the cosmos, and understanding this process, understanding how stars live and die, is not just about astronomy, it is about understanding where we came from and why we exist at all. So the next time you look at the stars, remember this. They are not eternal. They are temporary, and their deaths are not tragedies. They are transformations, because every ending in the universe is also a beginning, and the story of the supernova is the story of everything. We have established that stars die when they run out of fuel. But what is that fuel, and how does it power something as enormous and as bright as a star for billions of years? The answer lies in one of the most powerful processes in the universe, nuclear fusion. This is the engine that drives every star. This is the force that has kept our sun burning for 4.5 billion years. And this is the process that will one day stop, leading to the death of every star in existence. Let me take you inside a star, not metaphorically, literally. Imagine you could journey into the core of the sun. You would have to travel through 700,000 kilometers of boiling plasma, through layers of unimaginable heat and pressure, until you reached the very center. And there, in a region no larger than a quarter of the sun's total radius, you would witness something extraordinary. Hydrogen atoms, the simplest and most abundant element in the universe, are being transformed into something else entirely. They are being fused together, and in that fusion, energy is born. But why hydrogen? Why does every star begin its life burning this specific element? The answer is beautifully simple. Hydrogen is everywhere. It makes up about 75% of the normal matter in the universe. When stars form from collapsing clouds of gas and dust, hydrogen is the dominant ingredient. It is the raw material, the starting point, the first fuel. And it is also the easiest element to fuse. which is why stars spend most of their lives burning it. Now here is where things get interesting. Hydrogen, in its natural state, is a simple atom. One proton in the nucleus, one electron orbiting around it. Under normal conditions on Earth, hydrogen atoms remain intact, but inside a star, conditions are anything but normal. The temperature at the core of the Sun is 15 million degrees Celsius. The pressure is 300 billion times the atmospheric pressure at sea level. Under these conditions, something remarkable happens. The electrons are stripped away, completely. What remains are bare hydrogen nuclei, naked protons with nothing surrounding them. And when you pack billions upon billions of these protons into a small space, under extreme heat and pressure, they start to collide. Normally, protons repel each other. They are positively charged, and like charges repel. This is basic physics. But at the core of a star, the speed and energy of these collisions are so high that the protons overcome that repulsion. They smash into each other with enough force to merge, and when two protons fuse, they form a heavier nucleus. This is nuclear fusion, and it is not a gentle process. It is violent, chaotic, and extraordinarily energetic. When hydrogen nuclei fuse, they create helium, the second lightest element. But the mass of the helium nucleus is slightly less than the combined mass of the hydrogen nuclei that formed it. Where did that missing mass go? It did not disappear. It was converted into energy. And this is where Einstein's most famous equation comes into play. Energy equals mass times the speed of light squared. The speed of light is already an enormous number. Squaring it makes it incomprehensibly large. So even a tiny amount of mass, when converted into energy, releases an astronomical amount of power. This is what powers the Sun. Every second, the Sun converts 600 million tons of hydrogen into helium, and every second, 4 million tons of matter are converted into pure energy. 4 million tons. Gone. Transformed into the light and heat that reaches Earth 8 minutes later. That energy is what allows plants to grow. It is what warms the oceans. It is what makes life possible. And all of it comes from fusion happening in a region smaller than the distance from the Earth to the Moon, buried deep inside a star 93 million miles away. But fusion does more than produce light. It produces pressure. Outward pressure. Remember the war I described earlier? Gravity pulls inward. Fusion pushes outward. The energy released from fusion creates radiation pressure, a force so powerful that it holds up the entire mass of the star. Without fusion, the Sun would collapse under its own weight in minutes. Fusion is not just the source of light, it is the source of stability. It is what keeps the star alive, and this process can continue for billions of years, as long as there is hydrogen to fuse. Our Sun has been fusing hydrogen for 4.5 billion years, and it has enough fuel left to continue for another 5 billion. But that fuel is finite. Hydrogen does not last forever, and when it runs out, everything changes. Now let me explain what happens next, because this is where the story gets even more dramatic. When the hydrogen in the core is exhausted, fusion stops. The outward pressure disappears. Gravity, which has been waiting patiently for billions of years, finally wins. The core begins to contract, and as it contracts, it heats up. The temperature rises so high that a new kind of fusion becomes possible. Helium fusion. The helium nuclei that were created from hydrogen fusion now start fusing together, forming heavier elements like carbon and oxygen. But here is the catch. Helium fusion requires higher temperatures and pressures than hydrogen fusion. It is harder to sustain, and it produces less energy. So the star must burn hotter and faster just to maintain the same level of outward pressure. For stars like the Sun, this phase lasts only a few 100 million years. For massive stars, it lasts far less. And when the helium runs out, the process repeats. Carbon fuses into neon, neon into magnesium, magnesium into silicon, silicon into iron. Each stage burns faster. Each stage produces less energy. Each stage brings the star closer to its inevitable end. This is the life cycle of fusion. It is a countdown, a slow march toward death. And for massive stars, that march ends abruptly. Because once the core is filled with iron, fusion becomes impossible. Iron cannot be fused into anything heavier without consuming energy instead of releasing it. The moment a star's core turns to iron, the fusion stops entirely, the outward pressure vanishes, and gravity, unopposed, crushes the core in less than a second. That collapse triggers the explosion we call a supernova, but we are not there yet. Before we talk about the explosion, you need to understand just how extraordinary fusion is. It is not just a process, it is the reason anything exists. Every element heavier than hydrogen was created by fusion inside stars. The oxygen you breathe, the carbon in your cells, the calcium in your bones, the iron in your blood. All of it was forged in the cores of stars through fusion, and the heaviest elements like gold and uranium were created in the violent explosions that mark the end of a star's life. Fusion is creation. It is transformation. It is the universe building itself, one atom at a time. And understanding fusion is understanding the origin of everything. Without it, there would be no stars, no planets, no life. The universe would be a cold, dark expanse of hydrogen and helium, unchanging and lifeless. But because fusion exists, because stars can transform simple hydrogen into complex elements, the universe is rich, dynamic, and full of possibility. So when you feel the warmth of sunlight on your skin, remember this. That warmth is the echo of fusion happening 93 million miles away. It is energy that began as hydrogen nuclei colliding in the core of the sun, released as light, traveling through space, and finally reaching you. You are connected to the sun through fusion. You are connected to every star in the sky. Because the atoms in your body were once inside a star, fused in its core, and scattered into space when that star died. Fusion is not just the engine of a star, it is the engine of existence itself. And now that you understand how it works, you are ready to understand what happens when it stops. Because when fusion ends, the real drama begins. Fusion has stopped. For billions of years, the star has fought against gravity, using the energy from nuclear fusion to hold itself up. But now, the fuel is gone. The core is filled with iron, an element that cannot be fused without consuming energy. There is no outward pressure left. Nothing is pushing back. And gravity, patient and relentless, finally claims its victory. What happens next is one of the most violent events in the entire universe. The star does not fade quietly. It does not dim slowly. It collapses. And then it explodes. Let me walk you through this moment, because it happens faster than you can imagine. The core of a massive star, a region about the size of Earth, is suddenly unsupported. Fusion has ceased. The outward radiation pressure that held the core up for millions of years vanishes in an instant. Gravity pulls everything inward, and I mean everything. Electrons, protons, neutrons. The entire core begins to collapse at nearly a quarter of the speed of light. In less than 1 second, a core the size of our planet is crushed into a sphere roughly 20 kilometers across. 20 kilometers. Smaller than most cities, the density becomes so extreme that matter itself is squeezed beyond recognition. To give you perspective, imagine taking the entire mass of the sun and compressing it into a sphere the size of Manhattan. That is the kind of density we are talking about. A single teaspoon of this matter would weigh billions of tons. The atoms are not just compressed, they are destroyed. Electrons are forced into protons, creating neutrons. The core becomes a solid ball of neutrons packed so tightly that it behaves like a single atomic nucleus. This is a neutron star in the making. But the collapse does not stop smoothly. It overshoots. When the core reaches this incomprehensible density, it suddenly resists. The neutrons push back. They refuse to be compressed any further, and in that instant the collapse rebounds. Violently, the core bounces, and that bounce sends a shockwave ripping outward through the star at thousands of kilometers per second. This shockwave is so energetic, so powerful, that it blasts away the outer layers of the star entirely. Millions of times the mass of Earth are hurled into space in a matter of seconds. The star explodes. This is a supernova. but calling it an explosion almost feels inadequate. A supernova is not just bright, it is the brightest event in the universe aside from the Big Bang itself. For a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars. If you were observing from another galaxy millions of light years away, you would see a new point of light appear in the sky, blazing brighter than everything around it. And then, over the course of weeks or months, it would fade. But the light you are seeing is not just light. It is the death cry of a star that has burned for millions of years. Now, let me tell you what makes this explosion even more remarkable. It is not just destruction, it is creation. Everything we have talked about so far, fusion in the core, hydrogen becoming helium, helium becoming carbon, carbon becoming oxygen, all of that happened inside the star during its life. But there is a limit to what fusion inside a living star can create. Elements heavier than iron require more energy to fuse than they release. They cannot be made through normal stellar fusion. So where do they come from? Where does gold come from? Where does silver, platinum, uranium, and all the other heavy elements come from? They come from supernovas. In the unimaginable heat and pressure of a supernova explosion, conditions become extreme enough to forge elements that could never exist otherwise. Neutrons are blasted into atomic nuclei at such high speeds that they stick, building heavier and heavier elements in fractions of a second. This process, called rapid neutron capture, creates nearly every element heavier than iron. Gold, lead, thorium, all of it is made in the chaos of a supernova. Every gold ring, every platinum catalyst, every uranium atom used in nuclear reactors. All of it was created in the final moments of a dying star. And here is something even more profound. The explosion does not just create these elements, it scatters them across space. The shock wave from the supernova travels outward at thousands of kilometers per second, plowing through the surrounding gas and dust. It sweeps up material, it compresses clouds, it triggers the formation of new stars. The remnants of the dead star, enriched with heavy elements, become the building blocks for the next generation of stars and planets. This is how the universe evolves. This is how complexity increases. Stars die so that new stars, and eventually planets and life, can exist. Think about that. The calcium in your bones was created in a supernova billions of years ago. The iron in your blood was forged in the core of a massive star, and then blasted into space when that star exploded. The oxygen you are breathing right now, the oxygen that keeps you alive, was made inside a star and released into the cosmos through a supernova. You are not just made of stardust, you are made of supernova dust. Your atoms have traveled across the galaxy. They have been part of gas clouds, part of asteroids, part of the early Earth, and now they are part of you. This is not metaphor. This is fact. Every atom in your body, except for hydrogen, was made inside a star or in the explosion of a star. Without supernovas, there would be no heavy elements. Without heavy elements, there would be no rocky planets, no water, no organic molecules, no life. Supernovas are not just cosmic fireworks. They are the engines of creation. They are the reason we exist. But supernovas do more than seed the universe with elements. They also leave behind remnants. When the outer layers of the star are blown away, the core remains. And what happens to that core depends on the mass of the original star. For stars between about 8 and 20 times the mass of the Sun, the core becomes a neutron star. A neutron star is one of the densest objects in the universe, a sphere 20 kilometers across with more mass than the Sun. Gravity on the surface is so strong that if you were somehow standing there, you would weigh billions of times more than you do on Earth. If you dropped an object from 1 meter above the surface, it would hit the ground at millions of kilometers per hour. Some neutron stars spin rapidly, hundreds of times per second. As they spin, they emit beams of radiation from their magnetic poles. If those beams sweep across Earth, we see pulses of light, like a cosmic lighthouse. These are called pulsars. They are among the most precise clocks in the universe. Astronomers use them to test theories of gravity and even to search for gravitational waves. But neutron stars are not the only remnants. For the most massive stars, stars more than 20 or 30 times the mass of the Sun, even neutron pressure cannot stop the collapse. The core continues to shrink. It passes the point of no return. It becomes a black hole, a region of space where gravity is so strong that not even light can escape. The star has not just died, it has removed itself from the universe. Its mass is still there, warping space and time, but the star itself is gone, hidden forever behind an event horizon. Supernovas mark the end of a star, but they are also the beginning of everything else. They forge the elements, they trigger star formation, they create neutron stars and black holes, they enrich galaxies with the material needed for planets and life. They are death and birth happening simultaneously, and understanding them is understanding how the universe works at the most fundamental level. So, when we talk about supernovas, we are not just talking about explosions. We are talking about transformation. We are talking about the cycle of matter and energy that has been repeating for billions of years, creating the universe we see today. And now we are going to go even deeper. Because not all supernovas are the same. There are different types, different mechanisms, different outcomes. And understanding those differences will take us even closer to the cutting edge of astronomy. We have established that supernovas are among the most powerful explosions in the universe, but here is something that might surprise you. Not all supernovas happen the same way. Not all dying stars explode through core collapse. And not all stellar remnants are neutron stars or black holes. The universe has multiple pathways to destruction, and each one tells a different story. Understanding these differences is crucial, because the type of supernova determines what gets left behind, what elements are created, and how the explosion affects the surrounding space. So let us explore the different types of supernovas and the strange objects they leave in their wake. First, let me introduce you to the two major categories of supernovas. They are called Type 1 and Type 2. And the distinction between them is not arbitrary. It is based on what astronomers see when they study the light from these explosions. Type 2 supernovas show hydrogen in their spectra. Type 1 supernovas do not. That single difference reveals something profound about how the star died. Let me explain. Type 2 supernovas are the ones we have been discussing. These are core collapse supernovas. They happen when massive stars that are at least 8 to 10 times the mass of the Sun, run out of fuel and collapse. The outer layers of these stars still contain hydrogen, so when the explosion occurs, that hydrogen is blasted into space. When astronomers analyze the light from the explosion, they see hydrogen lines in the spectrum. That is the signature of a Type 2 supernova. These are the violent deaths of the giants, the stars that spent their lives burning bright and fast. But Type 1 supernovas are different. They do not come from massive stars collapsing. They come from white dwarfs. And that changes everything. Let me explain what a white dwarf is, because this is where the story takes a fascinating turn. A white dwarf is the remnant of a smaller star, a star like our Sun. When stars like the Sun run out of hydrogen, they do not have enough mass to trigger the fusion of heavier elements. Instead, they shed their outer layers, creating a beautiful structure called a planetary nebula. What remains is the core, a dense ball of carbon and oxygen about the size of Earth but with the mass of the Sun. This is a white dwarf. It no longer undergoes fusion. It no longer produces energy. It simply sits there, slowly cooling over billions of years. But here is where things get interesting. If a white dwarf is part of a binary system, if it has a companion star orbiting nearby, it can steal material from that companion. Gas from the companion star spirals onto the white dwarf, gradually increasing its mass. And this is where the danger begins. White dwarfs have a mass limit. It is called the Chandrasekhar limit, named after the Indian astrophysicist Subrahmanyan Chandrasekhar, who calculated it. The limit is about 1.4 times the mass of the Sun. If a white dwarf exceeds that limit, it can no longer support itself. The pressure becomes too great, and instead of collapsing into a neutron star, something else happens. The entire white dwarf undergoes runaway nuclear fusion. Imagine this: carbon and oxygen packed into a sphere the size of Earth, suddenly ignite. Not gradually, all at once, the entire star becomes a nuclear bomb. Within seconds, the white dwarf is completely obliterated. No remnant is left behind, no core, no neutron star. Just an expanding cloud of debris travelling outward at thousands of kilometers per second. This is a Type 1, a supernova, and it is incredibly important for astronomy. Why? Because Type 1 supernovas are remarkably consistent. Since they all occur when a white dwarf reaches the same mass limit, they all release roughly the same amount of energy. They all reach roughly the same peak brightness. This makes them what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. Type 1, supernovas allow astronomers to measure distances across the universe. In fact, observations of distant Type 1, supernovas, in the late 1990s led to one of the most shocking discoveries in modern cosmology. The universe is not just expanding, it is accelerating. That discovery earned the Nobel Prize in Physics in 2011. But let us return to Type 2 supernovas, because this is where the remnants become truly exotic. When a massive star collapses and explodes, the core does not vanish. It remains. And what that core becomes depends on the original mass of the star. For stars between roughly 8 and 20 times the mass of the Sun, the core becomes a neutron star. We have discussed neutron stars briefly, but let me give you a fuller picture of just how strange these objects are. A neutron star is a sphere about 20 kilometers in diameter. That is roughly the size of a city. But packed into that tiny volume is more mass than the entire Sun. The density is so extreme that a single teaspoon of neutron star material would weigh about 1 billion tons. If you could somehow bring a teaspoon of neutron star matter to Earth, it would punch straight through the planet and out the other side. The gravity on the surface is so strong that if you were standing there, you would weigh billions of times more than you do on Earth. The escape velocity, the speed you would need to leave the surface, is about 1/3 the speed of light. And here is something even stranger. Some neutron stars spin rapidly. When the core of a massive star collapses, it conserves angular momentum. Just like a figure skater spinning faster when they pull their arms in, a collapsing star spins faster as it shrinks. Some neutron stars rotate hundreds of times per second. Hundreds. These are called pulsars, and they emit beams of radiation from their magnetic poles. As the neutron star spins, those beams sweep across space like a lighthouse. If one of those beams points toward Earth, we detect a pulse of radio waves. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, and astronomers initially called them LGM signals, standing for little green men, because the pulses were so regular they seemed artificial. But neutron stars are not the end of the line. For the most massive stars, stars that are 30, 40, 50 times the mass of the Sun or more, even neutron pressure cannot stop the collapse. The core continues to shrink past the neutron star stage. It crosses a threshold called the Schwarzschild radius, the point of no return. Once it passes that boundary, nothing can escape. Not matter, not light, not information. The core has become a black hole. Black holes are perhaps the most mysterious objects in the universe. They are not objects in the traditional sense. They are regions of space-time where gravity is so strong that the fabric of space itself is warped beyond recognition. At the center of a black hole is something called a singularity, a point where density becomes infinite and the laws of physics as we understand them break down. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape. If you cross the event horizon, you would be pulled inexorably toward the singularity. There is no force in the universe that could save you. Time itself behaves strangely near a black hole. If someone watched you fall in from a safe distance, they would see you slow down as you approach the event horizon, eventually appearing to freeze in time. But from your perspective, you would fall through normally. You would simply never be able to send a signal back out. So, let me summarize what we have learned. Not all stars die the same way. Smaller stars fade into white dwarfs. Medium stars like the Sun shed their layers and leave behind planetary nebulae. Massive stars explode as Type II supernovas, leaving behind neutron stars or black holes. And white dwarfs in binary systems can explode as Type I supernovas, leaving nothing behind at all. Each type of supernova enriches the universe with different elements. Each one shapes the surrounding space in different ways, and each one provides clues about the life and death of stars. But there is one more twist to this story, one more layer. Because while we have been studying supernovas in our local cosmic neighborhood for decades, astronomers have recently pushed the boundaries of observation further than ever before. Using the most advanced telescope ever built, they have detected a supernova so distant, so ancient, that it occurred when the universe itself was barely formed. And that discovery is rewriting what we thought we knew about the early cosmos. We have traveled through the life and death of stars. We have seen how fusion powers them, how gravity destroys them, and how their explosions seed the universe with the elements needed for planets and life. But all of this knowledge comes from studying stars in our cosmic neighborhood, stars that died relatively recently in cosmic terms. What about the very first stars? What about the supernovas that occurred when the universe was young, when galaxies were just beginning to form, when the cosmos looked nothing like it does today? For decades, those ancient explosions remained beyond our reach. The light from the earliest supernovas was too faint, too distant, too redshifted for our telescopes to detect. But that changed in 2025, and what astronomers discovered has left them stunned. Let me set the stage. The universe is 13.8 billion years old. For the first few 100 million years after the Big Bang, there were no stars, no galaxies, no light. The universe was filled with hydrogen and helium gas, dark and cooling. Then slowly, gravity began to pull that gas together. The first stars ignited. These were not stars like our sun. They were massive, hot, and short-lived. They burned through their fuel in just a few million years and then exploded as supernovas. Those first supernovas were the most important events in cosmic history because they created the first heavy elements and triggered the formation of the next generation of stars. But we have never seen one, until now. On March 14th, 2025, an alert went out to astronomers around the world. A gamma-ray burst had been detected. Gamma-ray bursts are the most energetic explosions in the universe, aside from the Big Bang itself. They release more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. They are rare, unpredictable, and incredibly bright. This particular burst was designated GRB 250314A, and within hours, astronomers pointed the James Webb Space Telescope toward the source. Let me explain why this was significant. Gamma-ray bursts come in two types, short bursts and long bursts. Short bursts last less than 2 seconds and are caused by the collision of neutron stars or black holes. Long bursts last more than 2 seconds and are associated with the collapse of massive stars. They are, in essence, the birth cries of supernovas. GRB2 503114A lasted about 10 seconds. It was a long burst. That meant somewhere in the distant universe, a massive star had just exploded, and the James Webb Space Telescope was about to capture it. Now, here is where the story becomes extraordinary. When Webb analyzed the light from the burst, astronomers measured something called redshift. Redshift tells us how much the universe has expanded since the light was emitted. The higher the redshift, the farther away and the older the source. The redshift of GRB 250314A was measured at approximately 12. That corresponds to a time when the universe was only 730 million years old. 730 million years. That is just 5% of the current age of the universe. This was not just a distant supernova. This was one of the earliest supernovas ever to occur. Let me put this in perspective. The light we are seeing from this explosion traveled for over 13 billion years to reach us. When that star exploded, the universe was unrecognizable. There were no planets, no life. Galaxies were small and chaotic. The intergalactic medium, the space between galaxies, was filled with neutral hydrogen gas that blocked most light. The universe was literally opaque. This period is called the era of ionization because the first stars and galaxies were just beginning to ionize that gas, making the universe transparent for the first time. Detecting anything from this era is extraordinarily difficult, and detecting a supernova is nearly impossible, yet Webb did it. But Webb did more than just detect the gamma-ray burst. It confirmed the supernova itself. Let me explain why this matters. Gamma-ray bursts are brief. They last seconds or minutes. But supernovas are different. They brighten over days or weeks, reach peak brightness, and then fade over months. If you want to confirm that a gamma-ray burst was caused by a supernova, you need to observe the afterglow. You need to see the supernova light curve, and that is exactly what Webb captured. Using its infrared instruments, Webb detected the fading light of the supernova. It saw the explosion itself. Now, here is something truly remarkable about this observation. Light does not travel instantaneously. It moves at a finite speed, and as it travels through an expanding universe, its wavelength gets stretched. This is called cosmological redshift. The light that left this supernova as ultraviolet or visible light has been stretched so much that by the time it reaches us, it is infrared. That is why only Webb could see it. The Hubble Space Telescope, as powerful as it is, cannot detect infrared light at these wavelengths. Only Webb has the sensitivity and the technology to observe the universe at this scale. But there is another effect at play here, one that is even more mind-bending. Because the universe is expanding, time itself appears to run slower for distant objects. This is not science fiction. This is relativity. When astronomers observe the light curve of this supernova, they see it evolving more slowly than a nearby supernova would. The explosion that took weeks in the star's own reference frame appears to take months from our perspective. Time dilation caused by cosmic expansion means we are watching this supernova in slow motion. We are literally seeing time stretched across billions of years. And here is the kicker. This is not the first time Webb has detected an ancient supernova. Just months earlier, Webb observed another supernova at a redshift of 10, corresponding to an age of about 800 million years. That was the previous record holder, and now Webb has broken its own record. The James Webb Space Telescope has not just found the earliest supernova ever observed, it has demonstrated that it can routinely detect these ancient explosions. It has opened a new window into the early universe. But detecting the supernova is only the beginning. What astronomers really want to know is what the supernova looked like. How did it compare to supernovas we see today? Was it different? Did it produce the same elements? Did it explode the same way? These questions are critical because the first stars were fundamentally different from modern stars. They formed from gas that contained almost no heavy elements. No carbon, no oxygen, no iron, just hydrogen and helium left over from the Big Bang. Without heavy elements, these stars could grow far more massive than stars today. Some of them may have been 100, 200, even 300 times the mass of the Sun. And when they exploded, they should have looked different. But here is what shocked astronomers. The supernova they observed did not look different. Its light curve, its brightness, its behavior, all matched what we see from supernovas in the nearby universe. It looked modern. And that raises profound questions. Why does a supernova from the dawn of time behave like a supernova from today? Does this mean the first stars were not as different as we thought? Or does it mean that supernovas are more universal than we imagined, governed by the same physics regardless of when or where they occur? Webb also detected something else, something faint, a red smudge in the data. This is the host galaxy, the galaxy where the star lived and died. Seeing the host galaxy at all is extraordinary. Most galaxies at this distance are too faint to observe, but the supernova explosion illuminated the surrounding region, allowing Webb to capture a glimpse of the galaxy itself. This is a game changer. By studying these host galaxies, astronomers can learn about the environment in which the first stars formed. They can measure the mass of these early galaxies. They can study their chemical composition. They can piece together the history of the universe, and there is more. Gamma-ray bursts produce afterglows, faint emissions that last for days or weeks after the initial burst. These afterglows can be used as backlights to study the intergalactic medium. As the light from the afterglow travels through space, it passes through clouds of gas. Those clouds absorb specific wavelengths of light, leaving absorption lines in the spectrum. By analysing those lines, astronomers can determine what elements were present in the early universe. They can map the distribution of matter. They can trace the process of reionization. Gamma-ray bursts and their associated supernovas are not just explosions. They are cosmic probes, tools for exploring the universe at its youngest and most mysterious stage. This discovery is not just a milestone. It is the beginning of a new era in astronomy. Webb has proven that it can detect the earliest supernovas. It can study their properties. It can observe their host galaxies. And in doing so, it is rewriting our understanding of cosmic history. The first stars are no longer beyond our reach. We can see them die. We can study their remnants. And we can finally answer the question, how did the universe go from darkness to light? We have reached the end of our journey through the life, death, and rebirth of stars. We have seen how fusion powers them, how gravity destroys them, and how their explosions create the elements that make up everything we know. We have explored the different types of supernovas and the exotic remnants they leave behind, and we have witnessed the James Webb Space Telescope achieve something extraordinary, capturing the light from one of the earliest supernovas ever to occur, an explosion that happened when the universe was barely 730 million years old. But now comes the most important question. Why does this matter? What does this discovery tell us about the universe? And how does it change our understanding of cosmic history? Let me start with what astronomers expected to find. The early universe was fundamentally different from the universe today. When the first stars formed, they were made almost entirely of hydrogen and helium. There were no heavy elements because heavy elements had not been created yet. Without carbon, oxygen, nitrogen, or iron, the chemistry of star formation was completely different. The first stars, often called population 3 stars, were predicted to be massive, extremely massive. Estimates suggest they could have been 50, 100, or even 300 times the mass of the Sun. Stars that massive burn their fuel incredibly quickly. Their lifetimes are measured in millions of years, not billions. And when they die, they should explode differently. Here is why. A star's composition affects how it evolves and how it dies. Modern stars contain about 2% heavy elements. That might not sound like much, but those heavy elements play a critical role. They allow stars to cool more efficiently. They affect the opacity of the star's outer layers. They influence how energy is transported from the core to the surface. The first stars had none of this. They were pure hydrogen and helium. Theory predicts that such stars would be hotter, brighter, and more unstable. When they exploded as supernovas, those explosions should have been more energetic, more chaotic, and fundamentally different from the supernovas we observe today. But that is not what Webb found. The supernova detected at a redshift of 12, the one associated with gamma-ray burst, looked remarkably modern. Its light curve, the way its brightness changed over time, matched the light curves of supernovas in the nearby universe. Its peak brightness was consistent with what we expect from core collapse supernovas. Its spectral features, though redshifted into the infrared, showed the same basic patterns. This was not an alien explosion. It was familiar, and that has left astronomers scratching their heads. Why does a supernova from the dawn of time look like a supernova from today? There are several possible explanations, and each one has profound implications. The first possibility is that the first stars were not as massive as we thought. If early stars formed with masses closer to 20 or 30 times the Sun, rather than hundreds of times, their explosions would naturally look more like modern supernovas. But if that is true, it means our models of star formation in the early universe are wrong. It means we need to rethink how the first generation of stars came into existence. The second possibility is that supernovas are more universal than we realized. Perhaps the mechanism of core collapse and the resulting explosion are so fundamental that they look the same regardless of the star's composition. Perhaps the physics of gravity, pressure, and energy release override the chemical differences. If that is the case, It tells us something profound about the laws of nature. It tells us that the universe operates under consistent rules, even in its most extreme environments. The third possibility is that we are not seeing a population 3-star at all. Perhaps by 730 million years after the Big Bang, the universe had already gone through at least one cycle of star formation and death. Perhaps earlier, supernovas had already enriched the gas with heavy elements, and this star was part of the second or third generation. If that is true, it means the very first stars exploded even earlier, and we have not detected them yet. It means Webb needs to look even deeper, even farther back in time. Now let me tell you why this discovery matters beyond just understanding supernovas. The early universe was in a phase called the era of reionization. After the Big Bang, the universe cooled and became filled with neutral hydrogen gas. That gas absorbed most light, making the universe opaque. You could not see through it. But when the first stars ignited, their ultraviolet radiation began to ionize that hydrogen, stripping electrons from atoms and making the gas transparent. This process transformed the universe from dark and opaque to bright and transparent. It allowed light to travel freely through space. It made galaxies visible. Without reionization, the universe would still be dark. But reionization is not well understood. We do not know exactly when it began. We do not know how long it took. We do not know which objects contributed most to the process. Was it the first stars? Was it early galaxies? Was it supermassive black holes? The answer matters because it determines how structure formed in the universe. It determines how galaxies grew. It determines the timeline of cosmic evolution, and supernovas play a critical role. When massive stars explode, they release enormous amounts of ultraviolet radiation. They ionize the surrounding gas. They create bubbles of transparency in an otherwise opaque universe. By detecting early supernovas, Webb is helping us map the process of reionization. It is showing us how the universe became the universe we see today. And there is more. Webb also detected the host galaxy of this supernova. That faint red smudge in the data is not just a galaxy. It is a time capsule. It is a snapshot of what galaxies looked like when the universe was 5% of its current age. By studying these early galaxies, astronomers can measure their masses, their star formation rates, their chemical compositions. They can compare them to galaxies today and trace the evolution of cosmic structure. This is not just astronomy. This is cosmic archaeology. We are digging into the past, uncovering the origins of everything. But perhaps the most exciting implication of this discovery is what it tells us about the future. Webb has now detected multiple supernovas from the early universe. It has shown that gamma-ray bursts can be used to find and study these ancient explosions. And it has demonstrated that the afterglows of gamma-ray bursts can serve as backlights to probe the intergalactic medium. This is a new technique, a new way of exploring the universe. Astronomers can now use gamma-ray bursts as beacons, shining through the early universe and revealing the structure of matter along the way. Think about what this means. Every time a gamma-ray burst is detected, astronomers can point Webb at it and study the supernova, the host galaxy, and the intervening gas clouds. They can map the distribution of elements across cosmic time. They can trace the buildup of metals from one generation of stars to the next. They can watch the universe evolve. And because gamma-ray bursts are visible across the entire observable universe, this technique works at any distance. Webb can study supernovas from any era, from the earliest moments of star formation to the present day. This is not just a discovery, it is a revolution. For the first time, we have the tools to study the deaths of the first stars. We can see how they enrich the universe with heavy elements. We can watch how they triggered the formation of the next generation of stars and galaxies. We can trace the chain of events that led from the Big Bang to the formation of planets, life, and ultimately us. Every atom in your body was once inside a star. Every atom was created by fusion or by a supernova explosion. And now, we can see those explosions happening in real time, billions of years in the past. So what comes next? Webb will continue to observe gamma-ray bursts. It will continue to detect early supernovas. It will continue to study the host galaxies and the intergalactic medium. And with each new observation, our picture of the early universe will become clearer. We will learn how the first stars lived and died. We will learn how galaxies formed and evolved. We will learn how the universe transformed from darkness to light. And in doing so, we will answer one of the oldest questions humanity has ever asked. Where did we come from? The story of supernovas is the story of creation. It is the story of transformation. It is the story of how the universe built itself, one explosion at a time. And now, thanks to the James Webb Space Telescope, we are witnessing that story unfold. We are seeing the universe in its infancy. We are watching the first stars die. And we are finally understanding how everything we know came to be. This is not just science. This is cosmic storytelling. And the next chapter is just beginning.